Earlier, we defined heat as an energy that transferred from one body to another as a result of temperature difference. We have three mechanisms of heat transfer, and first to discuss is conduction. Conduction occurs within a body or between two bodies in contact. Let's say if you hold one end of a copper rod and place the other end in a flame, the end you are holding gets hotter and hotter, even though it is not in direct contact with the flame. Heat reaches the cooler end by conduction through the material. On atomic level, the atoms in the hotter region have more kinetic energy on the average than their cooler neighbors. They jostle their neighbors, giving them some of their energy. The neighbors jostles their neighbors, and so on, through the material. The atoms themselves do not move from one region of material to another, but their energy does. Heat transfer occurs only between two regions that are at different temperatures, and the direct of heat flow is always from higher to lower temperature. The material that permits the transfer of thermal energy between bodies is called conductor, and the materials that prevent the transfer of heat between bodies is called insulator. This figure shows a rod conducting material with cross-sectional area of A and length of L. The left end of the rod is kept at temperature of TH, and the right end of the lower temperature TC. The left end of the rod is kept at temperature TH and TC, so heat flows from left to right. The sides of the rod are covered by an initial insulator, so no heat transfer occurs at the side. Let's say that's the case for this one. So when a quantity of heat Q is transferred to a rod in a time, the rate of heat flow is called Q over T. So this rate is we call heat current. We denote H as the heat current. So we have here our formula to getting the heat current, which is equal to K times A, wherein K is our thermal conductivity of a material. So each material has its value for thermal conductivity. And A is for the cross-sectional area of the conducting material, where TH is the temperature at the left, or with the one with higher temperature, minus TC, which is the cooler temperature, over L, which is the length of the conductor. So the ratio of temperature difference and the length is we call temperature gradient. Now let's have an example problem. When excessive heat is produced within the body, it must be transferred to the skin and dispersed if the temperature of the body interior is to be maintained at a normal value of 37 degrees Celsius. One possible mechanism for transfer is conduction through the body path. Suppose that heat travels through 0.030 meter of path in reaching the skin, which has a total surface area of 1.7 square meter and a temperature of 34 degrees Celsius. Find the amount of heat that reaches the skin in half an hour. So we're looking for the heat that being transferred to the skin. So we're looking for Q. So we know that Q over T is equal to heat current. So if we multiply the time and the heat current, we will get the value for the quantity of heat. And using our formula that H, or heat current, is equal to K times A times TH minus TC over L. So we have the value of A, which is T, 1.7 square meter. The value of temperature, the higher temperature is 37 degrees Celsius and the lower one is 34 degrees Celsius. The length is 0.030 meter and time of half an hour. So what is the thermal conductivity of skin? So the thermal conductivity of skin is 0.2 joules per second per meter per Celsius degree. So again, it's your assignment to look for the thermal conductivity of other materials. Now let's substitute the value of area, which is 1.7 square meter. The temperature difference is 37 minus 34 Celsius degree all over L, which is 0.03 meter. And half an hour or 30 minutes is equal to 1,800 seconds. Now, let's have the cancellation of units. So we cancel the second, Celsius degree, and the unit per length. And the unit that will be retained is joules. So we know that heat is an energy and the unit for energy is joules. So calculating this, we will have the value or the result of 6.1 times 10 raised to 4 joules. So it's important to be careful with units. Now, let's have your test your understanding by solving this problem. Suppose we have two bars are separated. So we have a copper bar here and a steel bar. So look for thermal conductivity of these two materials. And one end of each bar is kept at 100 degrees Celsius, which is the left side, and the right side is at 0 degrees Celsius. So what is the total heat current in the two bars? So our hint for this one is to get the heat current of the individual material. Then get the sum of the total heat current for both materials, then you will have the result.